Today we will be looking at several demonstrations around center of mass and how the position of center of mass is linked to the stability of an object. But first, what is center of mass? Center of mass is a balance point in object where all the mass of an object seems to be concentrated. For example, if we take this cylindrical rod and if we want to find the center of mass of this cylindrical rod, then we need to find its balance point where we are able to balance it. So to find the center of mass, I need to find a point where this rod will perfectly balance. So here, somewhere here we see this is a point where this rod is perfectly balanced on my fingers. So this is the center of mass of this cylindrical rod. Since this rod is symmetrical and has a constant density, it is somewhere coming in the middle of the rod, which is also its geometrical center. And if we have a circular object like this, the center of mass will be somewhere here where we are able to balance it here. You must have seen the trick of interlocked fork balancing on a glass through a toothpick or a matchstick. Why it is able to balance? So how this combination was able to balance on the glass? First of all, this is a symmetrical system, and also the extended arms of the fork have actually moved the center of mass downwards somewhere on this central line where the toothpick was touching the glass. So hence it was able to balance. So remember this rule 1, that center of mass not necessarily have to be physically on the object. It can lie outside the object, as was happening in this combination. Let us take another example of this 2D figure. Let us call it as a KSS man and start putting some weight down. And if I try to balance it on my finger, you see I am easily able to do so. Let me try with a stick, balancing it on a stick. I am even able to do on a small stick. So why am I able to balance it so easily? Because like in the fork, it has an extended weight down, which has shifted the center of mass from somewhere here down to somewhere here. And the pivot is on this line of the center of mass. So we come to the rule number 2. If the pivot is above the center of mass, then the system will be balanced or can be in the equilibrium. Now if you shift the weights above and try to balance it either on a stick or on my finger, it is no more balancing because now the center of mass has shifted upwards and it is tipping over. Another way to understand this is, suppose I want to tip over this object. You see this object, it has a center of mass all below. So hence it is under balance, it is stable. To tip it over, I need to raise the center of mass to a level where it start tipping. But if I do it, flip this object and try to balance it, I am even not able to do that because the center of mass has now shifted upwards and it is easily going down. So this leads to rule number 3. If the center of mass is to be lifted, the system is stable. The further it has to be lifted, the more stable the system becomes. So in case of our KSS man, to make it tip over, we have raised the center of mass by moving the weights above. And it is no more a stable system. And the pivot here, where we want to try to pivot, is below the center of mass. So hence we are not able to balance it. To make it balance, we have to move the center of mass below the pivoting system. There are a number of toys I made to explain this principle. This is a tiger balanced on your finger. Why it is able to balance? Because it is lighter from above and all the weight is below. The center of mass has shifted somewhere below on this line, below this pivoting point. So the pivot is above the center of mass. So this is a balance system. Using the same principle, you can even balance the pencil on your fingers. You see, the center of mass has actually moved down because of this weight hanging, and it lies somewhere on this line, which is below the pivot line. This is another toy, the bald-headed eagle, which is able to balance on the beak. If you see this system carefully, you will see lot of weight are extended below, which has moved the center of mass somewhere here on this line. And the pivotal point is above this center of mass. So hence this bald eagle is able to balance on the beak. So this gymnast is able to balance on a thin wire. You see the extended weight which has shifted the center of mass down somewhere here. And even if I give a good shake, it is not falling. It is pivoting here on the same line of the center of mass. The same principle goes for this gymnast, which is balancing on a wire, which has an extended weight, making the center of mass move down, and the pivot point is above the center of mass. Hence it is in a stable system. Let us now see some real life examples where we use center of mass. Racing cars are designed to have a broad base and low height, hence lowering the center of mass so that the car does not topple over while taking sharp turns at high speeds. Double-decker buses are specially designed. The engine chassis and the running gear are all low down, and the top half of the bus is mainly empty space. The center of mass is remarkably low down. This stops the bus from tipping over. High jumpers arc their back so that their center of mass goes below the bar, and because of this, they can clear the bar without having their center of mass go as high as the bar, and so they need less force to do it. Or in other words, with the same force they can clear the higher bars. Have you noticed the postures of the sumo wrestlers? This postures helps to lower the center of mass so that they are not easily tipped over by the opponents. I am leaving you with all the toys to watch and enjoy. Thank you.